Welcome to part 4 of solving mazes with reinforcement learning. Before we get started, and we're going to be working on the actor model in this video, I want to go ahead and admit that a lot of the code from the actor, in fact, most of the code of the actual actor model, is taken directly from another implementation. I did not write this myself. It's going to be from Pranjal24's GitHub here, and I will link this in the video description. It's actually a really interesting implementation. He parameterized a lot of things and actually had a lot more code than I needed for this, and slightly different use cases. But the version of the actor class we're going to be writing is going to be almost a direct re-implementation of this Gaussian policy. So the other side effect of that is that I will be narrating it. I did not write every line of this, and I cannot explain it in the same detail as the person who would. So we're going to go ahead and get started, but just know if you want sort of the original, you can go find it here. And then you'll even notice in the README MD, he's even crediting that this is a reimplementation of this soft actor critic paper. So if you've been in software for any time at all, borrowing is the name of the game, and that is what we're doing here. So with that in mind, let's go ahead and we are going to create our actor class here. So class actor off of nn.module, just like we did the critic. And we're going to define the init function. As usual, passing in self. We'll need num inputs, num actions, hidden dimensions, action space is none. We'll pass in a checkpoint directory. We'll call it checkpoints. And we are going to give it a name and call it actor network. All right. So we'll do a super actor self. And we're basically just, as usual, calling the super class init in nn.module to set everything up correctly. Init and your parens there. All right, and then we're going to set up a couple of linear layers. Linear 1 equals nn.linear, num inputs, and hidden dim. And that's going to end up being a 250, or no, I think we're going to end up using 512 neurons in that hidden layer. Equals nn dot linear, hidden dim. So this is your sort of central, fully connected layer. And then we're going to take mean linear dot linear, hidden dim, and actions, or num actions is what we called it. All right. Here we will do take the log self.log std linear equals nn.linear hidden dim and num actions. Self.name equals name, just kind of setting up our standard variables. Self.checkpoint dir equals checkpoint dir, again for saving things later. Self.checkpoint file equals os.path.join. Self.checkpoint dir. And name plus underscore SAC. And then just like before, we are going to apply the weights init here. So self.apply weights init. All right. Finally, if action space is none, self.action scale equals torch.tensor, self.action bias equals torch.tensor, else, so just kind of telling it what to do if there's no action space passed in, self.action scale equals torch.float tensor, action space high minus action space low divided by 2. That dot is important since we're working with floating points. What we're doing here is effectively scaling the action that the network is going to produce by the size of the environment or the action space. So, you know, how broad the action space can be. And then we'll do the same thing here. Self.action bias equals torch.float tensor. Action space dot high, just like before, plus, this is a plus, not a minus this time, action space dot low, and divided by 2. All right. Next, we're going to need some of the same helper functions. So we're just going to go ahead and grab both of these save checkpoints and bring them down here so we don't have to retype them. And now we can get into the forward and sample methods. So def forward, self state, x equals, and just like we did in the in the critic, we're just going to pass it through the layers. So f.relu, here's our nonlinearity, self.linear1 state, x equals f.relu, self.linear2 of x, and now we're just passing x through everything we defined before. So mean equals self.mean linear x log std, self.log std linear x, and then finally we are going to log std equals torch.clamp log standard, and then here we're going to use some of those variables we declared up here. So min equals log sig min, max equals log sig max, and then we're returning mean. Can't talk and type. I said returning, so I typed returning. So we are going to return mean and log std. All right, and then finally sample, self state, mean log std equals self.forward, and we'll feed it state, std equals log std, and we're going to exponentiate it. We're going to create a normal distribution with the mean and standard deviation we have. So that's going to be normal equals normal mean std. We are going to then sample from the distribution. I'm going to say x of t is normal dot rsample. We're going to apply the tanh activation function to the sampled values. So y of t equals torch.tanh x of t. And then we're going to scale and shift the action to match the environment's action space. So that's going to be action equals y t times self.action scale plus self.action bias. And then finally, we are going to calculate the log probability of the sampled action. I don't know why I said finally. We're nowhere near done. Got log prob x of t. All right. Then we are going to enforce some of those action boundaries. So that's going to be log prob minus equals torch.log self.action scale times 1 minus yt to the power of 2 plus epsilon. We're going to then take log prob and do a log prob dot sum 1, and we're going to say keep dim true. Type keep dim equals true. And usually you end up using keep dim when you don't want to accidentally collapse one of the dimensions, which torch will sometimes do to you. Mean equals torch.tan h. So we're passing in mean times self.action scale plus self.action bias. And then we're returning action log prob mean. All right, we're done with the sample method. Now we're going to define the to method. Self, and this is just anytime you do like a to and then feed it to a different device or something, we are overriding that method, and we're doing that in order to send the action scale and action bias to that device as well. So I'm going to say self.device or self and device. Self.action scale equals self.action scale dot to device. Self.action bias equals self.action bias dot to device. And then we're just returning, we're calling the super of our actor and self.to device. All right, and then we are done for now with our models. We're going to come back much later and add a predictive model for use with our Intrinsic Curiosity module. But for now, that is all of the models we're going to add. In the next video, we're going to go ahead and start working on the buffer class. Next video will be buffer, and then after buffer, we will start putting together the actual agent that'll be playing, trying to beat the maze. So we'll go ahead and end this here and pick up with the buffer pi in the next class, or in the next video.